Okay, so this is it's titled here EtherCAT Basics, but what I've done, I've taken a couple of different PowerPoints and put them together to make a more of a detailed overview. And I'm also going to keep stopping it to show some things live with Motion Perfect as well. But just to start out, the EtherCAT, obviously we do these EtherCAT masters. It's all running on a standard Ethernet port really. With as far as the master's concerned, there's no difference in the Ethernet port compared to a PC or anything else with a normal Ethernet port. EtherCAT is quite capable of running from a PC or a Linux master with just standard Ethernet port technology. The earlier controllers we've done, like this MC4N and the MC664, they actually use an FPGA to generate the telegram. So we did go for our own solution on this. So the Ethernet telegram itself that's produced for the EtherCAT is produced in an FPGA. So it's all loaded into an FPGA, and it's just a shift register. It's clocked out at 100 megahertz. And so because of that, although I said EtherCAT masters can use a standard Ethernet port, we don't. In these controllers, we've actually made our own Ethernet port technology, if you like. So the transmitter and the socket are the same. So Ethernet itself, it has a transmitter chip called a PHY, and there is an Ethernet socket which has effectively transformers inside. So there's no DC coupling between what's inside the controller and what goes on the cable. It's done through transformers. So that's one of the beauties of Ethernet for doing this kind of communication. You can go out to your drives through a relatively hostile environment, if you like, and you won't get any coupling of 0 volt differences between the controller and the machine and all that stuff, because it's all AC and it's transformer coupled. So there's no DC coupling at all, which is really good. Now, having said that, we've got a picture of MC4N here. The MC6N and the Flex 6 Nano do have what is more common in EtherCAT masters. They have a standard Ethernet port. It's an Ethernet port in the processor, which comes out to the same socket. If you look at an MC6N, it looks the same as this. But they do use the more traditional way of doing EtherCAT masters. There is no special technology inside the controller at all. It's just an Ethernet port, and all of the stuff is done by software. And that does have an advantage. The performance of the Flex 6 Nano and the MC6N is higher than this MC4N on the EtherCAT side, simply because the software is driving an Ethernet port embedded in the processor. Whereas in the MC4N, the software has to load all of the information into this FPGA for it to be transmitted, and that takes longer. Yeah, so the EtherCAT, the new EtherCAT ports on the new controllers are much more efficient and will therefore handle more slaves, more data in a given servo cycle. So sort of improving everything. Okay, so what is EtherCAT? Okay, Ethernet technology, 100 base T. You can get EtherCAT now on a gig. When we used to go to the EtherCAT seminars, sort of about 5, 6, 7 years ago, they were making a big thing of the fact that they stick to 100 megahertz, because the technology is fairly low cost, it's very reliable, it's well known, and it's pretty low power. But obviously there's been pressures on EtherCAT to improve, faster and faster. So they now do 1 gig EtherCAT as well, but we don't do that. To go to a gig is quite a big step. The chips take more power, and obviously, you've got to be able to load the telegrams with data faster as well to make use of that time.
Does it come with a separate license as well?
I don't think so. Well, the thing about the master technology is that you don't need a license. Okay. The EtherCAT is only licensed on the slaves. So it's only slave devices that actually have to pay a license fee to back off for that. Okay. So as far as the masters go, we've been able to develop masters quite openly, and the EtherCAT technology group are very open about the standards and producing the information. So we've been able to do that quite freely without any problem. Anyway, Ethernet says there the standard I IEEE 802.3. But the issue with using Ethernet and why EtherCAT has been developed is because we do need, what it says there is real-time requirements. We need deterministic response times. We've got to get a telegram around to everybody within a servo cycle. There's also typically in a servo system or automation system, each node only has quite a small amount of data in it. So we don't need big telegrams to send the data. Now Ethernet itself actually has quite a big telegram, so we'll get that in a minute. And obviously people want the hardware cost to be kept low. That's still an issue. I think Reza will say that anybody selling an EtherCAT drive is always a price premium compared to a CAN bus drive, isn't it? Because the CAN bus technology costs almost nothing, whereas the EtherCAT chip, you've got to pay the license fee. The chip includes a license fee to Vekov. There's always a bit of a price premium. However, it is lower than some other technologies, and the attempt is to keep it fairly low. On the cable, we've got a typical Ethernet cable has 4 twisted pairs in it. EtherCAT only uses 2 of those. So if you buy an official EtherCAT cable, it only has 2 pairs in it. It doesn't use all 4. But you can use normal Ethernet cables, and basically it just doesn't use the other 2 pairs. And you can see there the arrows showing the data goes up 1 pair, up through the network, and then it gets reflected back and it comes back down the other pair, back to the master again. So when you've got a network like this, you can see that the one on the end on the right hand side doesn't have any connection to it, and the hardware inside the slave is designed such that if there's no connection on there, it automatically goes into a mode where it switches the telegram back down the cable. So the telegram will go, it goes up through the cable, one to the next, and then turns around and comes back down the cable through them all and back to the master again.
When you say it's normal, it goes on any other normal Ethernet cables, does that include a twisted pair?
Well, they are. Ethernet cables themselves are. Oh, I see, crossover.
Yeah, crossover.
No, you can't use crossover.
Okay.
They must be straight through. They must be straight through. But it's very rare to find a crossover cable now, isn't it? Because most switches do crossover themselves. Yeah.
With the laptops and
yeah. If you find a crossover cable, if I ever find one now, I just throw it in the bin. It's a pain. People talk about the topology and being able to do not just line topology, but star, tree, drop line. And that's the kind of thing that you can do. However, you cannot use a normal Ethernet switch, okay, because the EtherCAT telegram, it has a special way of transmitting itself around. It has to go up through all the nodes and then come back through all the nodes. So these special EtherCAT hubs or switches here, all they're doing is basically rerouting the telegram. So the telegram comes into here and gets sent out of that one, comes down this line, turns around and comes back, and then goes down that line, goes up this one, along that one, turns around and comes back, goes down there, turns around and comes back down this one, down that line, down there, down there, down there, and then finally back to the master. So if you imagined a little gremlin inside the controller looking down the Ethernet cable with a telescope, all he would see would be one long cable.
Right.
Because logically it's one long cable. These switches actually don't, it's not like an Ethernet switch where it actually does branch things off, send them down different links.
So how does that work with topologies then? So you've got, say, it's star or ring, and then there is another type of topology, and that sort of provides redundancy.
Well,
that actually.
Yeah, there is EtherCAT redundancy, you're correct, but we don't support that at the moment.
Right.
With EtherCAT redundancy, you would end up with 2 ports on the master. So there would be an outgoing, as you say, it would be, so if we go back to the picture there, it would come right round here, and the last one would actually have a cable back to the master again, and there would be 2 ports on there.
Okay.
And when you use redundancy, it's able to take the telegram from either side, so you can take it, you can break the link in the middle, and the others keep working. Yes. But we haven't got any support for that at the moment. It does come up with questions from customers from time to time. Can you do that? But, Okay, another feature of EtherCAT is, besides getting the telegram around everybody and back again, it needs to synchronize everything. So there's a system called distributed clocks. So the master in our case, there's a master clock generator, which in our case is the master, it's the controller. And that basically, we send out a telegram right at the beginning during the initialization phase. It will send out probably about 1,000 telegrams, each with a timestamp on. And each of the different devices looks at this timestamp and compares it with its own internal clock. And then after a while, they kind of work out what their time delay is between each node. So if you made a longer cable sort of between any two of them that had a greater delay, the next time you power up, it will actually compensate for that. And once it's got those delta times sort of programmed in, each time there is a telegram coming out of the master, every single slave should be actually clocking internally exactly the same moment in time to do its internal servo cycle timing. And the way that works out in hardware is that the EtherCAT slave controller inside the drive has an output which gives a pulse based on when this timing signal happens. And that pulse would then be used within that device to interrupt the processor. And then the internal processor in the drive, say, would then synchronize its internal servo cycle with that pulse coming out of the chip. Yeah. So if you have those three drives up there, each one of those should be, or will be, internally synchronized. It will start its servo cycle at exactly the same moment, even if I put different cable lengths on or put hubs in between or whatever. It sorts out that timing right at the beginning. So that's quite a big plus for EtherCAT, and it's necessary in a system as well, because we need to be able to master slave motion and things, so we need everything to be on the same time base. We've gone a little bit out on a limb again here, like we did with our early EtherCAT ports being built around FPGA hardware. With the distributed clocks, we went from the beginning as being the trio will be the master. Which is what is shown there. But most other EtherCAT masters, they use the first drive as the clock master. So in most diagrams you'll see like this one is the master, and all of those are slaves, and actually the controller itself is also a slave. So all the timing is done from the first drive. And this is because it's designed, as I said, around, you can build it into a standard PC. And a standard PC doesn't have the accurate timing we have inside our controller. So you need something with very accurate timing, i.e. the first drive,
So
to give the whole system the timing.
Does that mean for that style of system, the controller is the last node?
No, there's two concepts here. There's the EtherCAT master, which is still the controller, and then there's the clocks master. Yeah, you can have all sorts of different masters in EtherCAT, because if we did FSOE, failsafe over EtherCAT, there would then be a safety master, which is not necessarily the EtherCAT master either. So different masters for different needs. Now our MC4N, MC664X, the old MC464, the FPGA is clocked very accurately by an internal timer inside the controller. So when we build up the telegram and we send out the telegram, it is sent very, very precisely in time. Okay, so that's why we can be the clock master, because it is done that precisely. We actually had, Rich and I went to what's called a plug fest, and there was a guy there who the thing he brought along to try and out with everybody else's kit was an analyzer, and he put the analyzer on ours, and he said it was the best accuracy and stability of timing he'd ever seen on a master. What did we take then? We took I think it was the MC4N. MC4N, yeah. But the 664 would be the same. It's the same technology. The downside of that approach, of course, is that we cannot have the first drive as the clock master, because all of our synchronization is done to our internal servo cycle. We have no way of synchronizing to another external timing command. But the new generation, MC6N, Flex6 Nano, because they have just a software Ethernet port doing the EtherCAT, and all the EtherCAT is in software, there's no hardware involved, those can actually slave to another clock master. And there's a mode you can set the controller into to make the first drive the clock master. And we've had to do that with some applications. The new generation of Omron drives, it doesn't like us for some reason. It can't accept us being the clock master.
Okay.
So the only way we can start those is with the first drive as the clock master.
Is
Generally speaking, a servo drive would be, because of the generic, the general way a servo drive has to work with its internal servo cycles. It's controlling a torque loop in a certain time and a speed loop in a certain time. They do have very, very precise times. The clock in there. Inherently, they are precise. So them being the clock master is actually usually the best.
Makes more sense if it's.
So not say the best option. I say with our older controllers like the MC4 N664, because it is very precise as well, there's actually no difference between us being the master and the drive being the master in terms of timing and accuracy and stability. In fact, ours is probably better. Now, the reason we did it like that originally is because that's kind of how we've always done it. We had a Circos master before, and that we did the timing on that. We've had CANopen, and we've done the timing on that. So it's always been that the trio is the clock master on everything. And in fact, all of our modules that you fit onto an MC464, 664, that do the analog drives, they're all timed accurately as well. So when it reads the encoder inputs, it does them precisely on an interrupt signal that's sent through to latch all of those encoder readings. So that's all done with great precision as well. So because we've always had this very precise timed master, it seemed a natural thing to do. Now, when we've gone to the software version, where the MC6N Flex6 Nano have the EtherCAT done in software, it's more tricky then, because there is an interrupt that we have to follow, but the software has to actually respond immediately that interrupt happens in order to get the timing stable. And initially, the first version of the Flex6 Nano, the timing was all over the place. It was pretty bad. And what Rich had to do, and Fraser between them, they had to set it up so that when it finishes the servo cycle and does all its processing, for a few microseconds, it has to go into a little loop, literally just waiting for this clock tick, so that it can immediately start sending the telegram as soon as that clock tick happens.
Is this what happened with the power-up that you were testing before, that synchronizing this servo cycle or something with the latest firmware?
No, that was another issue.
Oh, that was
another issue. Yeah, that was something quite different. I say, and that was with the 464 as well.
Yes.
Because the 464 has this hardware EtherCAT. I'm talking about the Flex6 Nano, which has a software EtherCAT, and the MC6M, which has a software EtherCAT. So we've had to do some tweaks to our software to make it as precise as possible. But probably because it is a software-driven event, or a hardware-driven software thing, it wouldn't be as precise as the drive now. So the drive's clock master would be more precise than the trio, but not by much. Yeah.
So that's the choice now with the new controllers. You could be the master.
You can make.
Or it's the first drive.
It's always the first drive. Yeah.
Is it the difference being clock master? Because I think we didn't talk about this one. The M-force that you see in on the motion blueprint is from the controller.
Yes.
But there would be a significant difference between the M-force and the drive.
Well, when you say significant, yeah, there is.
See
The FE is different because of
the following.
Yeah, the following is different. That's nothing to do with distributed clocks. That's to do with the fact that I'm trying to think which slide to look at. So if you imagine that we're sending the demand position out this way, okay, and then coming back that way is the measured position back from the drives. That all happens in one cycle, yeah. One telegram goes out and then sends out and comes back. So we've sent the latest demand position, but the drive sending us back, it hasn't used that yet, yeah. the drive sending us back its internal measured position compared to the previous cycle's demand position, because it hasn't had time to process the new one yet. It happens so fast. So we always have at least a 1 cycle delay in the MPOS. And because our following error is literally DPOS minus MPOS, that delay is seen as an increasing following error, which isn't really there. So you have to look at the drive's following error to see the true following error. Okay, so there's an Ethernet telegram. So if you look at all that lot, you can ignore most of it, but just focus on the data. Okay, so the other stuff is mandatory. It has to have that other stuff to make it an Ethernet telegram. The data, minimum size is 46 bytes. Okay, so the overall telegram has a minimum length, if you add all those up, 46 plus the other stuff. And the reason why it's a minimum length is because Ethernet's designed to be transmitted on cables up to 100 meters long. And if you think about, I mean, electricity doesn't travel instantaneously, and these signals don't travel instantaneously. So if I've got a 100 meter long Ethernet cable and I've got one end where I've got a PC and it starts to transmit a telegram, and at the other end something starts to transmit a telegram at the same time, the way Ethernet works is it's basically got collision detection, where as it transmits its telegram, it's also listening to see if there's any interference. So the one that's sending it at one end will be transmitting its telegram and at the same time listening to say, okay, when I've set that bit high, yeah, it's high, that's low, yeah. So when the other telegram comes bouncing down the line and arrives at that one, we need that telegram to start interfering with the one it's transmitting so that it knows there's a collision. Do you see what I mean? So in the time taken to go from 100 meters away down to here, I need that telegram to arrive before the last byte of my telegram's gone, so that I can say, oh, there's another telegram on the line as well, I better stop. Effectively it'd be like, if there's someone at the other end of the car park and we both shout hoy to each other, sorry, hoy, be appropriate if it was hoy, hey to each other, the speed of sound, if you, so say it's more than just hey, say it's a sentence, say, 1, 2, 3, 4, 5, 6, 7, and he says the same. If I get to 7 and I haven't heard his 1 due to the speed of sound, I don't know he's been speaking at the same time as me. Do you see what I mean? So unless you've been watching the mouth, yeah, but Ethernet's not so clever. So with Ethernet as a system, there is this minimum telegram size, because you can't send a very short one, because the chances are a very short one would come down the line and the other end wouldn't hear it before it had finished sending its telegram. And then it wouldn't know there'd been a collision. But there had been a collision, and then something in the middle listening to both of them would go, hey, what's going on? I don't know. So it's this thing about collision detection that actually dictates the minimum telegram size. So this was always one of the problems with using Ethernet technology for drives and motion control. When we had CAN bus, it was lovely, because CAN bus is, you send 8 bytes of data, and okay, it's relatively slow, but it has collision detection with arbitration that actually doesn't destroy the telegram. It actually, it can actually, the way CAN bus works, if it sees a high and a low on the line at the same time, the low wins. So the one with the lowest address always wins. So nothing's destroyed if two things transmit at the same time with CAN bus. The one with the lowest address wins, and then that data gets through anyway. But with Ethernet, if two things transmit at the same time, if they detect the collision, they both basically, that telegram's destroyed. They back off, and they have a different time delay, and one will start to transmit before the other, and then that telegram gets through. But you have lost data by doing that.
To lose the time in that moment.
Yeah. So that's the other thing. You can't have collisions in a EtherCAT system. It's not allowed. So this is why you can't add an EtherCAT wire to a switch and then put it on the main network, because collisions are not allowed. You can't have other data on an EtherCAT system. It must be all controlled. This is one of the main issues, that the data into a node, say you're doing it over CAN bus, you want to send a position which is 4 bytes and a control word which is 2 bytes, that's 6 bytes, and you want to receive back an actual position and a status word, which is also 6 bytes. So you only want 12 bytes of data. So to send that 12 bytes of data over Ethernet, which has a minimum of 46 bytes, well, what a waste. You know, you're sending this big telegram with a small amount of data on it. And if you have a 32 node system, there's no way you're going to send 32 separate telegrams to all of those devices. Okay, the master could send one telegram with all the data for all the devices, but each device would have to send its reply back as a separate telegram. So if you had 32 nodes, you'd need 33 telegrams, one going out to them all and 32 coming back. So that's just not practical. It's just not going to work. And we need to try and also utilize this bandwidth more intelligently. What EtherCAT does, it basically takes that one telegram and it sends it around all of its nodes. Now this is only showing one node, but basically the telegram goes out to whatever nodes are there. So it's a string of them. It will go round all of them and then come back down the wire the other way. And the hardware, the clever bit that Beckhoff developed with the EtherCAT slave controller is that as it passes through the node, there are no delays. It doesn't read the telegram, take the data off, and then retransmit it. It lets the telegram just trickle through, and as the bits go past that, it's counting the bits. It goes, right, that's my bit, that's my bit. Mm-hmm. And it also puts data back onto it automatically as well. It can stuff bits onto the data as it goes through. So the telegram never stops. It just goes round the whole ring without stopping. And each node knows which bit of that red slice there, a node would know that's my bit. I'm going to take the data off there and I'm going to stuff data back on, my actual position data back on.
So
in the same
I imagine it's like a slug of train with sections.
Mm-hmm.
I know I'm compartment 2.
Yeah.
When the train comes in, I'm going to grab whatever on compartment 2 and then put it back on compartment 8 because that's where I send back my data.
And the train won't stop. You're going to have to do that. You're going to have to run along and push the things in as the train's going through.
Okay.
But does it extract it from compartment 2 and then repopulate it within?
Yeah, it does. So
not over the top of the original data.
No,
it takes the data off and stuffs the new data on, more or less at the same time. But
That's the moment actually, based on the clock. I mean, the pulse, they do it at the same time.
They do it pretty much at the same time. Yeah.
So that the clocks can synchronize.
So when we have this 6 byte data we want, we don't need 12 bytes actually. We only need a compartment with 6 bytes because we're taking 6 bytes off and we're putting 6 bytes back on using the same compartment. So the only thing that causes a delay is any propagation delays down the cables and the small delays through. Each node will have a small delay. Obviously, you can't have no delay, but there will be a small hardware delay. But certainly not the sort of delay you'd have if I'm going to read all of this data in, process it, and then retransmit it. That would be far too big a delay to do that.
Is there any fiber optic way?
There is a fiber optic EtherCAT as well. Yes, but we've not started looking at that either. The fiber optic EtherCAT was designed and developed for a particular application Beckhoff did on ski slopes.
Okay.
So it transmits data between artificial snowblowers up the ski slope. And each one was like, I don't know, half a kilometre apart or something. So they needed a fiber optic system.
But of course it costs more.
Yeah. But Beckhoff have done quite a few of these sort of kind of bespoke applications, and because they're the inventors of EtherCAT, if there's something, we can't use normal EtherCAT, we'll invent something new, and then.
Wasn't Circos fiber optic?
Circos was fiber optic, yes, which we had masters for that. That was quite a good system. Yeah, it works well. And there is now Circos 3, which is the same thing over an Ethernet link. And you can also do Circos over EtherCAT. We do CANopen over EtherCAT, but they call it Servo over EtherCAT, but it's the Circos profile. They're not allowed to use the word Circos, but it is effectively Circos. Okay, so there we can see our like multiple telegrams there. So we've got 5 nodes we're sending data to, so there's 5 compartments to put the data in. in this single EtherCAT telegram. There's also a big yellow bit here I've marked, and that's called the mailbox. So you've got your cyclic data going in the red bits, in and out all the time, and the mailbox data is the bit where you might just say, okay, send me the value of register 51, and so you can send asynchronous messages through the mailbox to just go, okay, write this value into register 590, that kind of thing. So each mailbox transfer is basically the master puts some information in the mailbox and says, this is going to node number 6, and I want to read register 51, and then node number 6 reads that and goes, okay, I'll get register 51, I'll put the value back in, and that happens a few milliseconds later, and it puts it into the mailbox going back to the master again. So that one mailbox actually has to handle all of the slaves, so you can't broadcast to all of the slaves. You've got to say, okay, slave 1, slave 2, slave 3, each one an individual cycle of sending the data, getting the data back in one mailbox. So it is a restricted channel from that point of view. And each cycle, we've been doing an application for a customer in China, and they were egging us to get the cycle time down on this mailbox transfer, because they're trying to do a lot of stuff using what's called SDOs, which is your service data objects. And I think we got it down to sub 10 milliseconds. It can go down to about 5 probably, but there are, there's a delaying. You've got to get the data out to the drive. The drive has to process it and do something with it and come back. And each one of those is kind of, well, there's another millisecond, there's another millisecond. So it does take time. Okay, so that's all about Ethernet and EtherCAT as a technology. So when we're starting up a controller, what we're going to do. So in the approach we've taken is to try and make it plug and play. So each version of firmware has embedded into it some profiles for common devices. And when we started that approach, there were only about 20 servo drives on the market, so it actually was quite a cool thing to do, because we had every single servo drive in there. But now, of course, there's hundreds and hundreds of them, so we have some. We probably have the majority, to be honest, but there's new ones coming out all the time. So if you're lucky and your drive is actually in the database, then you can find it using this intelligent drives feature, which is go and browse the database. In fact, if I just so if you go into this bit here and then click browse database, then this is where you can see what you've got. So you've got all these different vendors down here. They're not all drives, some of them are I/O. Turk, for example, this is an I/O device down there. So you can see if it's an I/O device, it basically tells you not a lot. That's probably just a holding entry, actually. And it probably needs some setup to make it work. That wouldn't work out of the box, I don't think. But Eston, of course, we have a number in there already. We don't have the summer yet, but I guess that will be coming quite soon. The ProNet's there. And again, if we just look at that, you can see that we have the minimum. Each of our profiles, we start off with the minimum size where we've just got 6 bytes each way. And then you can go up different profiles. That adds the actual following error. That one adds touch probe. That one adds some digital I/O. And that's a slightly different pattern of digital I/O.
So the actual FE is from the drive?
Yes. Yes. Yeah. So this is setting up stuff actually in the PDO, in the cyclic data. So this particular one here, we've got, obviously there's only 6 bytes that way, but coming back the other way, we've got 4, 6, 7, 8, 9, 10. There's 10 bytes. So the little compartment has to be 10 bytes.
Right.
We don't use all of it going one way. We only use 6 of it, but it has to be 10 bytes in order to fit the biggest of the
I see.
of the two sizes. Yeah.
Okay. So what happens if we can't find the device that is not in our library?
Okay, I'll come to that in a little bit.
Okay.
Yeah, we'll cover that in a little while. So that's where that little diagram comes from. So in okay, so this bit's about starting up EtherCAT. So assuming you've got your drive connected and you know, everything's in the database, you can just basically start it up. You can either do that from the nice way from Motion Perfect here. So if I just close those down, if I do that button there, that will reinitialize the drives and it'll go through the different states. So you see it says pre-operational there, and then it says eventually safe operational. It's taking a little while. Okay, it's gone. It did go through safe op, we just couldn't see it. Too quick, exactly. So if you do that in the terminal though, from the Motion Perfect Terminal 0, you get this little report where it shows you the different states as it goes through. Okay, and what it's doing is in the initial state, when it first does that, that's where it sets up the distributed clocks. So it goes out and sends some telegrams out at the beginning and goes, okay, I can see all of these nodes. I mean, I've got 3 drives on there. I can see there are 3 nodes, and they're all reporting that they want distributed clocks to be set up. So then it does its distributed clock setup. Okay. Once it's finished that, it then goes to what's called the pre-operational state, and in the pre-operational state, then the mailbox is live, and the master can send configuration data to the slaves and receive information back if it needs to through the mailbox. So in initial state, all you have is literally a comms channel with accurate clocks, but you have no way to communicate to anything because there's no mailbox. But once you go to pre-op state, the mailbox is now there. It's not doing a cyclic transfers, but the mailbox is there and we can actually configure our drives. And usually what happens is that during the pre-operational state, that's where we do all the configuration. So we would set up PDO maps and things like that, and anything else that's required. And then once we finish that state, we can then tell all the slaves to go to the safe operational state. And at that point, the cyclic data is actually running. So we've got positions going out to the drives, we've got positions coming back, but we can't enable it. It's called safe op because the idea is you can't actually enable any axes or turn on any outputs or whatever you've got, and therefore you then need to go to the operational state where we're then ready to actually enable.
So now, during the init process, you're just checking in. Oh, who's in the loop?
Yeah, it's like who's in the loop, and
right.
Does anybody need a clock? Oh, you need a clock. Okay, we'll handshake and do all the clock stuff.
Okay, so that's why technically, if there's a drive that you don't recognize, it wouldn't pass the init stage.
It doesn't need to know that the drive configuration's in the database to do init. It just needs to know it's there, because at the low-level EtherCAT level, it will go, oh, there's a device. Okay, I don't know what it is yet, but we'll set it up anyway and get the clocks going. And then when it gets to the next stage where it needs to go pre-operational, it goes, oh, I've got no data for this, I can't set it up. Right. And therefore it gets stuck in init.
Okay.
Yeah.
Okay.
So it just stays there in init.
Through the pre-op because you can't really set the mailbox.
There was no configuration.
I don't know how much I need to prepare for the slug.
Exactly.
Right.
Exactly. Now our system, some systems, I think they would pause in safe op and then wait until things are enabled. But in our case, safe op is just a stepping stone. We always go safe op and then operational directly without stopping. So we never really stop in that, and unless you can force it in software if you want to. You can go through one step at a time. Okay, so that's we've got it started. Assume it's gone operational. So the profile we're using mostly is CANopen over EtherCAT. Now, some of you know CANopen. You know CANopen, don't you, Reza? Some of you a little bit. But CANopen basically works around a concept of having what's called objects. and each object has an address, if you like. It's got an index address and what's called a sub-index address. And the indexes are a 32-bit number, so it can go between 0 and FFFF, or 65535 if you want it in decimal. And the sub-index is a 1 byte value, so that can go between 0 and 255. So there's an opportunity to address an awful lot of registers if you need to. And really all they are, they're just register addresses inside the device. This actually only works if the device is intelligent. So, for example, our digital I/O devices on the Flex Slice range, that has an EtherCAT slave controller in it, and that EtherCAT slave controller directly accesses the I/O. There is no processor in that, so there's no CANopen over EtherCAT in this. It doesn't do COE. The only protocol it has is EtherCAT. So it's just very basic EtherCAT. So nothing else at all really. And then our typical drive that has the EtherCAT slave controller chip again, but that then talks to a microprocessor, and that then does all the clever stuff in and out of whatever it is. And it's this microprocessor with its memory that would have all the objects in it that you can then talk to and access. Yeah. So this protocol does require the device to have a processor and actually be communicated to. If it's just a basic I/O device, it just doesn't exist. So on our FlexSlice modules, there is a difference between a standard digital I/O device and an analog. For example, the analog I/O device has a processor in. So the analog I/O do have COE. The P375 does have COE. The new RTD and thermocouple devices will have processors in, so they will have COE. But the digital I/O, you want to be cheap, so you don't put anything in you don't need to. Just leave it.
That's what COA is.
Sorry?
CANopen over EtherCAT.
Yeah, COE is CANopen over EtherCAT.
No, CIA.
Oh, CIA. All right, that is the CANopen. Sorry, CAN automation, which is an organisation that controls CANopen. They're the guys who defined it, and they're the ones who manage it basically.
Oh,
So
the array of predefined.
yeah. So the CAN automation group is a German originated group, of course.
Is it like
It's the standard tags.
It probably has an IEEE standard against it, I expect. But the CIA is an organisation. It's like the EtherCAT technology group is an organisation. The Profinet group is an organisation that manages that particular protocol effectively.
That's why I said before that 6000 series is like the standard.
Yeah. So if you sign up to the CAN automation group CIA, you pay some money to be a member, and you can get hold of these different standards. So there's a basic standard for the protocol, and then there's a standard for drives, which is CIA 402. There's a protocol standard for I/O, which is CIA 401. That covers digital and analog, I think. And then there are many others. I mean, it covers all sorts of stuff. There's a protocol standard for navigation systems on yachts and boats and ships. There's a protocol standard for anything you can think of, really. Hair dryers, I don't know. Anyway, 402 is the one that we comply with. So the object numbers, I've written them in hexadecimal, which is how they're commonly seen. So the communication objects are the ones we're mostly interested in because they set the cyclic data up, and the standard CIO objects 6000 to 6FFF. Many drives actually they have what are called manufacturer specific ones, which are 2000, basically anything between 2000 and 5 FFF. These are manufacturing specific. And what that allows a drive manufacturer to do, and a lot of them do it, is on the drives you've got on the front, you've got like PN, blah, 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 different numbers.
Yeah.
They just mean, if they want to, they can say, right, starting with 2000, I'll map all my PNs into there. So PN 501 is 2000 plus 501, for example.
Okay.
Yeah, and then you've got most drive manufacturers give this sort of nice. Well, you just have to read their manual, so at least you know PN 200 is going to be $2,000 or $3,000. They sometimes do the 3,000 offset, and then the PN number added to it. However, Eston took a different view on that. If you look at the Eston mapping of PN numbers to objects, it seems to be quite random.
Very random.
They haven't applied any kind of standard offset. So you've got to look in the Eston manual and say, okay, so PN 704 is that object number. There's no kind of standard offset.
Hex 8000? No. I saw.
Yeah. So. Yeah. So basically, although it says 6000 to 6FFF, what happens in multi-axis drives is that 6000 is the first axis, and then 6800 is the second axis, 7000 is the third, 7800. So they use this standard offset. So this is axis 1, if you like, 2, 3, 4, 5, 6, and you can carry on your 9000 and 9800. That will give you 8 axes and 1 node. So this is where you have one drive with multiple, or one drive with multiple axes on it. So when you look at a typical 2-axis drive, you'll see 6000 as the range in the first axis and 6800 as the range on the second axis.
Okay.
But it's because it's in one node, so they have to be referenced differently. So I could say that, well, actually it's kind of true that 6000 and 6FF are the standard ones. It's just you're repeating them with an offset. So in fact, the truth is 6000 to 67FF is the range, and then it's repeated with an offset. Now the cyclic data stuff is set up with pointers. So anyone who knows CANopen would recognise these series here, 1600 and 1800, as being the pointers for setting your cyclic data going out and back. In CAN and CANopen using CAN bus, each of these objects can only be 8 bytes because a CAN bus telegram can only carry 8 bytes. So in a traditional CAN bus system, you'll see 8 bytes carried at 1600, and then another 8 bytes carried at 1601, and another 8 bytes carried at 1602, etc. Should they need that size of data, and they would be separate CAN bus telegrams. But in EtherCAT, we don't need that because we have one massive telegram. We can make it quite big, and all we need to know is how big the compartment is on our train. So we don't actually need to split it up into separate telegrams at all. But to sort of keep the standard going, if you like, and also it makes drive manufacturers who make CANopen drives, it makes them quite easy for them to transfer to EtherCAT. What they did was say, okay, you can keep your array of different addresses for telegrams that would be on separate CAN messages. And what we'll do, we'll add another set of pointers to allow us to point to those, and then they're all part of the big telegram. So that's what the two at the bottom do. The 1C12 or 1C13, those are additional pointers. You never see those in CANopen. They're an EtherCAT thing. So 1C12 would point to 1600, for example. Or if it's not 1600, it might point to 1603, if that's what they're using. So there's like a double pointer system here, where 1600 would point to, say, the control word, which is 606. Well, the control word 6040, and then 1C12 would be pointed to 1600. So it's like goes through two stages.
Is that like a subcategory of that?
It's not really a subcategory. It is a pointer to a pointer. So that's IO, but let's just quickly look at the drive situation. So So here we've got the object values 6040, which is the control word, and 60FF, which is speed command, okay, demanded speed. This is what we want to get the data into inside the drive, okay. And what we do, we set up a pointer to that in traditional CANopen by saying, right, the 1600 will be pointing to 6040 subindex 0, and 1600 subindex 2 is pointing to 60FF subindex 0. Okay, so that's how it would look in CANopen. But then to add it to the telegram, we then have to tell the telegram using 1C12 that it will be putting the data into 1600. So the data comes along the telegram here. We've got 6 bytes of data. No one knows what this data is. It's just 6 bytes, unless we tell it. Obviously, at the master end, we have to know that this is these 2 bytes here are the control word, and these 4 bytes here are the demanded speed. So we've set that up at the trio end and said, right, those bytes in the telegram are this. And when they arrive at the drive has to know that that's what they are as well. So these pointers allow the drive to say, okay, those 2 bytes there are, and because 1C12 is pointing to 1600 subindex 0, so subindex 1, those 2 bytes will go into there, and then 1600 subindex 1 says, those 2 bytes actually, I need to pass them on and put them into that object. So it actually comes from the telegram via that pointer, if you like, into the final destination, which is there. Seems like a bit of a kind of a contrived approach, really.
Then it's fine. What if it's 10 bytes now?
Well, you have to set up pointers to where those other 4 bytes are going to go.
So then it will be 16 or something like 1.
It could be. I mean, this is 1600 subindex 1, subindex 2. We could use subindex 3 and subindex 4.
So if it's larger,
yeah.
That
But it's quite possible. Some drives actually stick to the prescribed CAN bus limit of 8 bytes because they're just taking the CANopen software they had and putting it on EtherCAT. So in some drives, because we've got 6 bytes here already, if there was another 4 byte number, another 32-bit number, it would not be able to put it in 1600. It would have to put it in 1601 because in CAN bus that means you've got another telegram which gives you another 8 bytes.
How the Eastern operate?
The Eastern, I think, it allows you to make as many in one. It doesn't limit it to 8 bytes, so you just keep adding subindexes. Yeah, it seems to work. But when I've set these up, sometimes I just have to do it by trial and error, just to find out what works. Well, we did that the other day, didn't we, with that Mandy drive?
Yeah.
We just played around until we got it right, and yeah, some of it's just intelligent guesswork.
Yeah.
Just going back to that other slide, this is the same thing, but this is an I/O device. So in the I/O spec of CANopen, the CIA 401, normally you have 7,000 is the range of things going to outputs. And they've got 6,000 is the inputs, and 7,000 is the outputs. So in this case, the pointers 1C12 is still pointing to 1600, but it's got 6 subindexes, each one only 1 byte long. So each of these is 1 byte, and then they go through to the I/O, or the outputs in this case. So in I/O stuff is usually much more simple, and as I say, if it's a simple I/O device, it wouldn't even have, this mapping wouldn't really exist, because it wouldn't know what CANopen is. Okay, and then if you take all of that knowledge that I've just given you, and you then look again at the drive profile inside the controller, and you look at all those numbers, now they will mean something to you, because you say, oh yeah, there's 1600.01, that's 6040, and therefore that is that's the control word, and 607A is the target position.
The brackets.
The number in the brackets, that is the number of bytes.
Right.
Yeah. So these first ones are all single byte numbers.
Yeah.
Well, the way CANopen works in general is that you have to set all these registers to 0 first before you can configure them. So these first 3 are just setting the registers to 0, and then it can go through and configure them. The 1A100 set to 0 here. So this is 1C12 subindex 0. This is 1600 subindex 0. And what it does, it sets that to 0. That says, okay, right now I can set it up. So it puts subindex 1 to that value,
So those are
subindex 2
4
to
bytes,
that
yeah,
value,
those are 4 bytes.
and then it says, okay, 2 4-byte values. I've got 2 values, so therefore I need to put in this one, the value 2, because that's the number of values I put in it. Yeah.
Yeah, you define.
Yeah. So you define that as 2 because you've put in 2 things here. And say each of these are always 4-byte numbers because they're always that format. It's always the object, which is the first 4 digits,
Yeah.
the subindex, which is the next 2 digits, that 00, and then the last one is the size, and it's the size in bits.
So 4.
So 10 in hexadecimal is the same as 16 in decimal, so that's 16 bits. 20 in hex is the same as 32, so that's 32 bits. And you either just need to know that a target position is always 4 bytes, or you need to look it up from a manual. Or in fact, the ESI file you get from the device will contain this as well. Should tell you what size things are, and then you set this one up to 2 at the end.
Yeah.
Yeah. Yeah, it's just because you cannot set these. If this already has a number, it won't allow you to set these. That must be set to 0 to allow you to set the others up. Otherwise, it will reject it. So the last two, the 1C12 there has been set to 1600, and then there's only one of them. And 1C13 has been set to 1A100, and there's only one of them. And then the last one here is this 6060 is the mode of operation. So that an 8 means it's position mode. And you could, if you're dealing with a drive that needs more configuration, you can put any things here you want. So you could set up, drive gains or something if you wanted to during this pre-operational phase. So all of this is sent during the pre-operational state before it goes safe op.
And it's depend actually about how many bytes drive can provide for master. I mean, there is a limited memory inside the drive for the PDO setting.
At some point it may run out. I had a customer with an LTI drive, and he wanted to put more and more things in the PDO, and eventually the drive just rejected it. So no, I can't make a PDO that big.
So so we need to pick the high important one, put it in the PDO.
Yeah,
and the less important one do by SDO.
Exactly. And then the other thing you need to consider is that if you put quite big PDOs with a lot of data in, and then you add 10 drives to the controller, our poor controller has to handle all of that data 10 times over. So it actually increases the load on the controller a lot, much more than even the drive does. So you want to think about trying to minimize it as much as you can. Just have the necessary in there.
And this is also the big point of the multi-axis drive, that they're using same memory to drive 3-axis. So you have to care about it, If you want too many data to transact between the master and the drive. So there's a limitation in the multi-axis compared with the single axis. Because they're using the same memory size,
Yeah.
So this is
that would be
would meet in the CANopen.
A drive limitation.
Lots of time, Customers need more.
Yeah.
That's why
Exactly.
CANopen instead of EtherCAT.
So
No, this is from the drive viewpoint,
yeah. This now goes on to talk about debug, but what I want to do rather than carry on with this slide is, I think what we'll do is we'll look at these PDOs and answer the question, what do you do if it's not built into the database? We've got our 3 Eston drives there, but obviously they do exist, they're already there, so that isn't a problem for us. I should put a summer drive on there, shouldn't I, which doesn't have one.